Hello everyone, my name is Julio Guilindro and I'm going to talk about an operating systems project I've been working on. The project tries to solve a problem a car company has. The problem is that they want to implement an anti-collision systems to their cars. So they put two sensors. The first one being a laser sensor which calculates the distance to the nearest object. The second one taking into account that not all the streets are even and that they might have potholes in them, they decided to put a gyroscope on the car so they could calculate the inclination the car has, taking into account the x-axis as a reference. So they use this data to calculate the real distance to the nearest object. The frequencies of the sensors are not the same. That is another problem. We have to take into account that the laser sensor is twice as fast as the gyroscope. So the system, because it should be in real time, must provide the best estimate of the real distance to the nearest object in the shortest time possible. In order to pull this off, we have to take into account four things. First, we should read concurrently the data from the gyroscope and the laser sensors. Second, we should calculate the real distance taking into account the gap between the arrival of the data and also the geometry of the problem. Third, we should be able to start, terminate, or restart any of the sensors we want. Fourth, the system should be able to measure the response time between every data that is generated.
To solve the problem, I designed a real-time system for the calculation and reporting of the correct distance. The system consists in three main modules. The first one, the one that we're seeing here, is the process generator. The process generator receives a number of sensors that you want to spawn. It generates one process for each number of sensors that we have in the car. So, for instance, if we get three sensors to spawn, it will fork three sensor processes and it will create the process for one sensor, a process for the other one, and a process for the last one. So it will create n processes that we pass. The second one is a signal manager, which acts as a way to control the sensors. The signal manager allows the user to restart or terminate any of the sensors by listening to external signals sent by the user using a terminal. So, for instance, if we get a restore signal for the process with PID 1, the signal manager will go and check which is the process that it needs to restart, and it will kill the process that is currently running, and it will spawn a new process with a different PID. So, and for the termination signal, if we get a termination signal for the process PID2, it will go and check what is the process that it needs to kill, and it will terminate it instantly. The third module is a process which is constantly reading the values produced by the sensors. In this case, the sensors will be the processes created by the first module. Inside this process, there will be a validation for the frequency of the data from the sensors. This validation follows this flowchart. The flowchart begins by listening to the values for the values of the distance sensor and the gyroscope. If we get a value from each one of these sensors, we will set a switch on and return the angle value for each one of the sensors. If we get both switches on, then we will generate a pair of distance and angle and return it. As you can see, if we don't get any of the values for each sensor, we will keep listening for each one. But if we get a valid pair of values, we can generate a pair and return it. So whenever we have a distance angle pair ready, we will create one thread for each one of those pairs. The thread will calculate the real distance, show it on screen, and end itself. So it doesn't interrupt or block the next values that might come from the sensors, nor interrupt the reading or calculation of next pairs to come.
To avoid any race condition, the pairs of values that are sent between threads and the response times values are protected using mutex locks. The response time is calculated since the first value is created until the system finishes calculating the correct distance and showing it on screen. For future improvements, I was thinking of improving the data transfer between threads by implementing a shared data struct instead of using global variables, in order to avoid implementing mutex locks manually and possibly improving the response times. Also, we could implement not only two types of sensors, but many of them in order to get a much more accurate data to calculate the real distance as accurate as possible.
So we got some statistics to prove that our system is working as expected. Here we have our concurrent version of the system, which is the one that we implemented, and a non-concurrent version. The non-concurrent version doesn't use any threads or any processes. It just reads the values and calculates as they come. So we took 50 response times for each one of our programs, and we took those response times in seconds, and we calculated the mean. As we can see, the concurrent mean, the mean of the concurrent version, it's slightly lower as the non-concurrent one. They have a difference of 0.0 seconds, which it might not seem like a lot, but it is actually a really noticeable difference. As we can see on the graphs, we have the concurrent version graph, and those peaks are not that high as the ones in the non-concurrent version. As we can see, the non-concurrent version has peaks as high as 1 second, and on some of those really high peaks. But in the concurrent version, we have peaks that are not that high. They come and peaks of like zero point 0.5 seconds at most, and just this one that it's 1 second. But as we can see, there are more peaks that takes more time on the non-concurrent version than in the concurrent version. Watching these graphs and everything, we can say with assurance that our project works as expected and that everything is working fine. Thank you for your attention.